Before you trust any measurement, you need to answer this question. Is the variation you see coming from your process or from your measurement system itself? If your gauge is unreliable, every control chart, every capability study, and every process decision built on that data is untrustworthy. That is why measurement system analysis is one of the first things you should do in any quality improvement project. Hello everyone, in this video we are going to walk through the most widely used MSA method, the Gage R&R study, which stands for Gauge Repeatability and Reproducibility. You will learn core definitions about Gage R&R, how to plan the study, how to run it on the shop floor, and how to interpret the results so you can decide whether your measurement system is acceptable and you can know what you need to improve. Let us start with the definitions. What does a Gage R&R study actually measure, and why are we doing this in the first place? It all starts with variation. As you may guess, every process has variation. When you measure your parts, you see a spread in the results. But here's the key point. That spread is not pure part variation. What you see is actually a combination of the variation coming from the parts themselves and the variation added by your measurement process. This is the core idea behind the whole study. If you want to see your natural process variation, your measurement system variation must be small compared to the real process variation. Otherwise, the measurement noise hides what the process is actually doing. And measurement system variation does not come from a single source. Part of it comes from differences between operators, and part of it comes from the measurement equipment or method itself. A Gage R&R study investigates measurement system variation in these two components. The first is repeatability. Repeatability reflects the variation of the equipment or method itself. This is the variation you get when the same operator measures the same part multiple times with the same measurement instrument. If one person gets very different readings on one part, the gauge has a repeatability problem. The second component is reproducibility. Reproducibility reflects the variation between different operators measuring the same parts with the same instrument. If operator 1 reads very differently than operator 2, that difference is a reproducibility problem, and it usually points to differences in technique, training, or how the measurement method is defined. Together, repeatability and reproducibility make up your total measurement system variation. We then evaluate it in two ways. The first is comparing it against the total variation, which includes the process variation. The second is comparing it against your specification tolerance. The goal is simple. Measurement variation should be a small slice of the total or should be small compared to the tolerance span, so you can use the equipment to monitor the process and judge the performance. So here's a short definition of the whole concept. A Gage R&R study is a structured experiment in which several operators measure the same set of parts multiple times, so the total variation can be split into repeatability, reproducibility, and part-to-part variation, and you can judge with numbers whether your measurement system can be trusted. Let's move on to planning. A good planning determines whether your study is trustworthy. The standard crossed Gage R&R design uses 10 parts, 3 operators, and 3 trials, which gives you 90 measurements. You can adjust these numbers, but this combination is the industry default because it balances statistical power with practical effort. It is important that your parts represent the full range of your actual process variation. Do not grab 10 parts from the same box produced in the same hour. Pull parts from across the process spread, including parts near both specification limits if you can. If your parts are too similar, the study will unfairly blame your gauge because part variation will look tiny compared to measurement variation. So select parts that reflect your real variation span. Pick parts from different hours, different batches, different mold cavities, and so on. And also choose operators who actually perform this measurement in daily production. Do not use your best metrology specialist if the real measurements are done by line operators. Use the same gauge that is used in production and verify it is calibrated before the study. Now we come to the most important part of the whole study, the execution, before we move to the practical part. If this video is adding value so far, take a second to like it and subscribe. It really helps the channel reach more quality professionals like you. Now, back to work. Instead of just talking about it, we will do it together, step by step. Using the free measurement system analysis module on SigmaDesk, you can follow along at sigmadesk.app, and everything you see here works the same way for your own study. By the way, you can follow the same path with your own application, an Excel sheet, or any other software. The most important thing is to understand what we do. From the SigmaDesk dashboard, open the measurement system analysis module and click New Study. The first screen asks for three things: a study name, so give it something descriptive that you will recognize later. For example, shaft diameter gauge, study line 3. A gauge name, where you enter the exact instrument you're testing. For example, a digital caliper with its identification number, and an optional description for any special notes about the purpose or conditions. Do not skip these fields. 6 months from now, or when an auditor asks about the study, this header information tells the whole story of what was measured, with which gauge, and why. Next, you have two paths. If you already collected your measurements somewhere else, you can continue with your own dataset and paste it in. But since we are starting from zero, we choose continue with preset worksheet. And this is the path I recommend because the application builds the entire study structure for you. On the configuration screen, we enter our study parameters. Number of parts, 10. Number of operators, 3. Number of replicates, 3. Replicates is just another word for trials. Below that, you can rename your parts and operators. I suggest using the real operator names or initials instead of operator 1, 2, and 3 because it makes the results much easier to discuss with the team afterwards. And here's a detail I want you to notice. There's a checkbox called Randomize Run Order, and it is checked by default. Leave it checked. When this is on, it shuffles the measurement sequence within each operator, so nobody measures part 1, then part 2, then part 3 in a predictable line. This is important because if an operator remembers that part 5 measured 12.03 in the first trial, they will unconsciously steer toward that same reading in the second trial. The gauge will look more consistent than it really is, and your results will be too optimistic. Randomizing the order and keeping the part identities hidden from the operator protects the study from this bias. But just for this video, I will uncheck it so you can see the pattern in the worksheet more easily. Now, click Generate Preset Worksheet. And here's our worksheet. Look at the structure because this is how measurement data is organized in practice. Instead of a wide grid with one row per part, we have one row per measurement, 90 rows in total, and each row has a run order number, a part, an operator, and an empty measurement cell. The part, operator, and run order columns are pre-filled and locked, so you cannot accidentally break the study design. The only thing you type is the measurement value. Now you simply follow it from top to bottom. The first row tells you which operator measures which part. Hand that part to that operator, they measure it, and you type the value into the measurement cell of that row. Then the next row and the next. When the worksheet moves to the second operator, you switch operators and continue, row by row until all 90 cells are filled. In practice, you can keep SigmaDesk open on a laptop or tablet, right at the measurement station, and enter values as they are read. Or if that is not practical on your shop floor, collect the values on paper in the run order sequence and type them in afterwards. Either way, the person handling the parts and the sheet should ideally not be the person measuring, so the operator only measures and reads the number out loud without seeing the part labels or the previous results. A few rules while recording. Type each value exactly as the gauge shows it with all the decimals. Do not round, and no do-overs. If a reading looks strange, enter it anyway. That strange reading might be exactly the measurement system behavior you are trying to detect. You are testing the measurement system as it normally operates, not creating an ideal showcase. Once every measurement cell is filled, click Continue to Column Mapping. Because we use the preset worksheet, the part, operator, and measurement columns are already recognized, so there is nothing to fix here. If you chose to continue with your own spreadsheet data in the first step, this is where you would do the matching yourself. But there is one optional field, the tolerance limits. Enter the lower and upper specification limits of the characteristic you measured. This is what allows the analysis to calculate percent tolerance. In other words, how your measurement variation compares against your specification, as we mentioned earlier. If you skip it, You will still get the study variation results, but you will miss that second acceptance criterion we talked about earlier. It is time for analysis. There are two classical methods. The average and range method is simpler, but the ANOVA method is the modern standard because it can detect the interaction between operators and parts, which the range method completely misses. Every serious software tool uses ANOVA, so that is what we will focus on. And now everything is ready. Click Analyze Data and it runs the full analysis for you. In this part, we will walk through these results together and learn how to read every table and chart on the screen. The analysis is done and the results screen is in front of us. Let us read it together from top to bottom, and I will explain what every number means using the actual results from our shaft diameter study. The banner here is a great summary, but you should never stop at the summary. So let us move down to the Gage Evaluation table and understand it line by line. The table has four numeric columns. The first is the standard deviation for each source of variation. The second is the study variation, which is simply 6 times the standard deviation. Why 6? Because plus and minus 3 standard deviations covers about 99.7% of a normal distribution. So 6 standard deviations is the conventional window that represents the full spread of each variation source. You can learn more about this by watching the highlighted video in the corner. The third column is percent study variation, which compares each source against the total variation observed in the study. And the fourth column is percent tolerance, which compares each source against the tolerance width we entered during column mapping. Now the rows, the first row is total gauge R&R. This is the variation that belongs to the measurement system itself, the combination of repeatability and reproducibility. The second row is repeatability, the equipment variation. This is how much the readings spread when the same operator measures the same part several times. Here it is, 18.43% of study variation. The third row is reproducibility, the operator variation, and here it is only 7.96%. Repeatability is more than twice as large as reproducibility, so the gauge and the measurement equipment, not the operators, are the main source of measurement error. Our three operators agree with each other quite well. The instrument itself is the weaker link. This single comparison is what tells you where to look first if you ever need to improve the system. The fourth row is part-to-part variation, the real differences between the products themselves. It stands at 97.96% of study variation. This is exactly what you want to see. In a healthy measurement situation, most of the variation you observe should come from the parts, not from the act of measuring them. Our gauge is spending its effort seeing real product differences, not its own noise. And the last row is total variation, which is 100% by definition. Now, here's a question that confuses almost everyone the first time. Look at the percent study variation column. 20.08 plus 97.96 is clearly more than 100. Is the table wrong? No. Standard deviations do not add up directly. Variances do. If you square 20.08, you get about 403, and if you square 97.96, you get about 9,600. Add them together and you get roughly 10,000, which is 100 squared. So the columns are consistent, they just add in squares. Below the Gage Evaluation table, SigmaDesk also gives you the full ANOVA table and the variance components in collapsible sections, and then the 6 diagnostic charts. If you want to verify the mathematics or dig into the raw sums of squares, everything is there. But for the general evaluation, the Gage Evaluation table is where the answer lives. So let us now take these numbers to the acceptance rules and make the call. Now for the decision rules based on the AIAG guidelines that most industries follow. If percent gauge R&R is under 10%, your measurement system is acceptable. Between 10 and 30%, the system is conditionally acceptable. It may be tolerated depending on the importance of the application, the cost of the gauge, and the cost of improvement, but you should document the justification. Above 30%, the measurement system is unacceptable and must be improved before you rely on its data. Decide upfront whether your acceptance decision should be based on percent study variation or percent tolerance. If the gauge is used for process control and improvement, compare against study variation. If the gauge is used primarily for inspection against customer or design specifications, percent tolerance is the more relevant benchmark. Now you have the whole picture and you know how to interpret the results. Let us come to the next question. What if your study fails? The diagnosis depends on which component dominates. If repeatability is the biggest contributor, the problem is the equipment or the method. Look at gauge resolution, wear, fixturing, part clamping, and environmental factors like vibration or temperature. Sometimes the fix is as simple as a better fixture that locates the part the same way every time. If reproducibility dominates, the problem is between operators. That means the measurement procedure is ambiguous, standardize the method, define exactly where on the part to measure, how much force to apply, and how to read the scale. Then retrain everyone to that one standard and repeat the study. Now we have come to the end. A trustworthy measurement system is the foundation of everything else you do in quality. If you want to run your own Gage R&R analysis without expensive software, try the Measurement System Analysis module on SigmaDesk. It is completely web-based and you can go from raw data to a full ANOVA report in minutes. The link is in the description. If this video helped you, give it a like, subscribe for more practical quality engineering content, and I will see you in the next one.